In this experiment, the ball bearing travels back and forth on the track, and a 9-volt battery powers the coil that produces a magnetic field at the center of the track. Whenever the ball bearing travels through the magnetic field, the flux linkage is changed in the ball bearing. This induces electrical fields in the ball bearing and thus induces eddy currents. These eddy currents produce magnetic fields of their own, which interact with the magnetic field produced by the coil at the center of the track. These forces created between the magnetic interactions between the eddy currents in the coil increase the overall energy of the ball bearing and thus increase the length of time that the ball bearing oscillates back and forth on the track. This is the results of a simulation of the second design iteration of the project that I ran in FEMM. As can be seen, the magnetic field is very strong near the center of the coil, and it quickly gets weaker as you go out from the center. And this is the track. It's approximated to be a semicircle in the simulation. It's as the ball bearing travels back and forth on the track, the magnetic flux linkage changes in the ball bearing since the field is stronger near the center and weaker out from the center of the coil. This change in magnetic flux is what induces the electric fields inside the ball bearing and produces the eddy currents that interact with the magnetic fields that the coil produces. The following clip shows the performance of the initial iteration of the project, where the large coil is hooked up. And this is how the ball bearing and track system performed after I added a new coil with a smaller radius to increase the magnetic flux density on the track. The magnetic fields produced by each of the coils respectively can be approximated by using the Biot-Savart law, H equals Ni over 2A, where N is the number of turns. The coil that measures approximately 0.045 meters in diameter was measured to have approximately 1.22 amps of current flowing through it with the 9-volt battery applied, while the 0.08 meter coil had approximately 1.02 amps when the 9-volt battery was applied. The magnetic flux density can be calculated for the 0.045 meter coil as being 16.77 Gauss in free space, and the 0.08 meter coil can be calculated to have a magnetic flux density of 7.88 Gauss in free space. So the smaller coil produces a significantly stronger magnetic field than the larger coil. This can be used to explain why the performance of the system was better with the smaller coil than with the larger coil.